Hello. I don't think we're going to get many more, so I'm going to start off. My name is Jan Griebsch, or Jan Griebsch, I would say in English, but I think the Polish people would agree that Jan Griebsch is much better. I'm here for one-on-one. The company is sponsoring this talk. When management asked me if I could speak here, I thought about it. What can I say? Nothing about the secret sauce, nothing about all the backwards things that exist in every IT organization. So something in the middle. What I thought might have value for the people here is not about the theory and the theoretical aspects of any particular authentication method, not about the kind of white paper niceties of certain authentication algorithms and so on, but a little bit about the kind of dirty details. So if you're not like a startup that does everything fresh, if you're not one of the really big ones that can throw money at everything, but if you're kind of in the middle, an IT company. And you've kind of heard that passwords are bad. There's a problem there. What can you do to mitigate the risk that threatens your customer accounts and your business by extension? So if you're such a client, then I guess this talk could be for you, because I'll be talking a little bit about the tale of the changes and the challenges that we had in our organization to approach this topic and improve on security in this aspect. It's my first talk here, so I don't know what's customary in terms of asking questions or anything. So I'd be happy to field questions anytime. Okay. All right. So in the background, there's a picture of the first attempts we made at the topic, essentially figuring out, well, there's information to be had in all the metadata, this kind of famous stuff that you see, right? Where do customers come from? How do they use your infrastructure and so on? And we figured, so if we focus, also for this talk, if we focus on security, not in the sense of locking up your data center or hashing your passwords, but rather in the sense of how do I prevent leakage and breaches and misuse through my APIs, then there's information to be had in metadata. And so one of the first things we looked at, how do our customers come? And this is actually a picture of our customers using our SMTP interfaces. So a large part of us is a mail company, as you know, and that comes with the additional challenge that mail SMTP IMAP POP is not a very rich interface, right? So you can't have tokens and cookies and all this kind of stuff easily. The remaining data is more interesting, and this is, like a plot where we looked at it and said, okay, what can we discern there? And I think black dots were IP addresses, and green dots were halo strings, and blue dots were user accounts, and so on. So pretty convoluted, as you can see. Okay, so that was one of the very first looks at it. But first again, motivation. The problem I stated, how relevant is it really? Well, from those articles, and I think it's nothing new, of course, to the people here. The industry has a problem there, right? And even the big ones have problems. And sometimes it's even really cutting into the bottom line, as with Yahoo and so on. When I was researching this, on a funny side note. You really know you have a problem when there's people forecasting the next breach. So then you know it's really prevalent in the industry. So why do those things happen? Obviously, your accounts have a value, and obviously there's nowadays an industry kind of trying to make money of hacked accounts, of leaked accounts, of credentials, and so on. So there was a nice article from I think Brian Krebs a year or two ago, detailing the dark corners of the dark web here. Found a site selling stuff. I think accounts and credentials on average for about 8.19 or so. 15 for banking and e-commerce credentials, and so on, and made quite a bit of money out of it. And actually this was a protected site, of course. Again, quite funny. The reason why this was in the end accessible and was found out, this particular page, because the seller there, the author, the hacker, or whatever you want to call him, what did he do? He reused his password. So that is kind of very typical thing in this field. Not only e-commerce and PayPal and so on have a value, but obviously also things like email and so on, because nowadays email accounts are often used kind of as a root account to your whole online identity. It is also used to reset other accounts and so on. So in the kind of dark economy, it's not quite as valuable usually in terms of bare money, but it's of course an interesting entry point to other valuable things. And if you look at it from a commercial point of view, the value that kind of white commercial companies like Facebook and Google put to those accounts is much higher. You can measure the revenue you have per account, and as you can see, accounts are quite valuable, in particular for companies who can exploit the commercial value well. And then, of course, there's a third point of view to this. How valuable is this to the owner? And of course, this is highly individual in nature. There's some academic work on measuring how much money people would pay to get, their account back, or how much money they would accept or to have their private data published. And usually, this is higher still than the commercial value. So those things are valuable, but catastrophes happen all the time. Why is that so? Because with all the research that's been put in there the last decade or so, with all the clever authentication and security mechanisms in the end, unless you have a very special use case, you have a very high value transaction, like I want to transfer all my money from one bank account to another or so on, you can't really economically use those expensive authentication factors. So you fall back on the standard. And the standard with passwords obviously is, it leaks all the time with break-ins, with breaches, with malware, with phishing, and so on. Also, the human nature comes into play there. Password complexity and entropy obviously is a burden on the users to manage. I think about 12% or so of users use password managers, whereas about 38% of users reuse their passwords. In shopping, in e-commerce scenarios, it's supposed to be even more. Then again, there's another 20% that don't directly reuse passwords, but modify it quite trivially. And also another academic result is about 70% of people use still the same password or don't change their password a year after it's been publicly breached. Okay, so this is basically the baseline, right? The password is always the basis, the basic mechanism to secure your account. And then, of course, there's multi-factor. What's the problem with multi-factor? Very easily said. The best in the business, so to say, is a reference. They quote and say about 10% of, not even 10% of our accounts, we've managed, after years of investing into it and pushing it, we've managed to protect with a two-factor. Okay, so seems to come out to some kind of nice choice there. What do you want to do? Run the risk of losing customers to breaches, to inconvenience if you burden them with elaborate security measures. What do you outsource your accounts to Facebook and have them have the problem, or do you invest more and more and in the end lose your shop kind of to security costs? So this is kind of the baseline I'm talking about. You have on the one hand you have passwords, everybody does it kind of thing, and then you have the high value scenarios. You have multi-factor in various colors and variations, and then you have all the big things, the big field in between, and there's no real good solution to it. In a landmark paper a couple of years ago, there was another proposal that was said, hey, but financial institutions and also some of the big players in the industry they have managed to push down the risk. They still have those kind of spectacular break-ins from time to time, but they survive. So how do they do it? Why haven't they gone bankrupt or anything? And they figured, well, we set the wrong goal. The goal is not to really the traditional assurance with a password and then you're in, but the goal is to change your coordinate system to say, well, we're okay if we have just a kind of sufficient amount of security. So in the sense here, if you look at the old tale from Little Red Riding Hood, I think in English it's called, right? With a wolf and says, okay, password. So nowadays you just accept, right, and say, yeah, good, the password is fine. Okay, so you just accept. What you should do instead is you should look at the many signals that you have and that you get for free, like the metadata, like the IP address, like the behavior, and so on. And then, of course, authentication is no longer a kind of black and white issue, but it becomes a kind of classification issue with gray areas and mistakes and false positives and so on. Okay, so passwords are still a signal, of course, but they're one signal amongst more and many signals. Okay, technically, how do you approach it? Again, a quote from somebody from Google from the beginning of 2018 said the key takeaway was modern password authentication requires a risk-aware and defense in-depth system. Okay, so what did he mean with that? Well, in-depth sounds like this maybe. So you start up observing your transactions and your data, you analyze it, then you model it with some kind of classification algorithm and evaluate it, and then you draw a conclusion from it, and you grant or deny a certain action, or maybe a login, or you challenge and you say, no, I'm not happy with what we're doing here. Can you help me improve the trust that I need to allow you this action? Well, this whole process certainly sounds quite a bit more involved and expensive than just asking for a password. So how expensive is it? And what do we need to overcome in terms of challenges to make it happen? Well, the first thing to observe is that the steps that you're taking here, they partially overlap with other business processes, other stakeholders. So at least in our company, we had, for example, business intelligence, who was very interested in looking at those things. The particular metadata we looked at for the beginning was data that we could always get. So I said that one particular challenge in our company was that we have a lot of APIs that don't transport a lot of data, like mail APIs. So we restricted ourselves to network data, IP blocks and so on, autonomous systems, locations and so on, annotations to IPs, and request data. So request data meaning behavior, time, actions, and so on. Also claimed request data like device and software stack data. Okay, and then we kind of went into the circle. And of course, in reality, you, as I said, you come from an existing IT infrastructure, and for us, it kind of looked more like this, the circle. So you have your users, and then they come through a bunch of devices, different devices, of course, and they come through a different, and they use different products, mail, file transfers, and so on. They shop, they go to the home page, they use upload files and smart drive and so on. And then, you have a bunch of kind of legacy IT systems that talk with each other to make those use cases happen. And out of those many, many different systems and all their interconnects, then you try and extract data to generate reports, to generate data for drill downs, for real-time monitoring, for notifications if something goes wrong. And you have a bunch of stakeholders, right, that kind of evaluate those reports. You have BI, you have abuse and security people, you have auditing and compliance, and of course you have operations. And so after kind of looking at this for a while, it became clear that there's no fixing this in terms of getting the circle completed. You have pairwise communication between the different systems. A lot of information is lost there. The metadata from the edge systems is usually not communicated to the backend systems. The different databases are usually not suitable to the type of analysis we want to do. They have issues with additional load, with stabilities. They all have different APIs. They often don't support historization. Then if you talk about more unstructured backends, logs, of course, they have all kinds of different formats. Their semantics are not defined. They're usually updated in batches, sometimes in daily batches. They have a mixing of concerns in them. So you have in traditional logs, you have the debugging stuff, you have the business intelligence, and so on. And they're organized by service and not by process. So then obviously what you would do is, okay, nowadays, okay, and this picture, of course, in reality is more involved than this. So in our company, we have about 1,000 different services, about 16,000 different systems, about 1,000 changes a month. We have different requirements on products, contracts, orders, ad campaigns, and so on. And so, yeah, this picture is a lot more complex. And so really the only way out there we saw is to separate the two and to separate the architecture for the core business processes from the architecture to transport all the metadata. And the obvious choice, the obvious choice there is to use a bus system. The obvious choice nowadays, it wasn't a couple of years ago, but we got it right for a change anyways, was to use Kafka there. Just one big, nice bus to transport it all, to also pull data together from different data centers. And it works quite well for us. We're having a peak of, I think, about 1 million events per second per data center. Our lead times are about 100 milliseconds or so in the 90% percentile. And technically, it's quite a nice system. So, but of course, the challenges don't quite stop there. So, so for example, now you've swapped all your different interconnects out for one big, nice event bus. But instead of having lots and many technical dependencies, now you have kind of more a hidden dependency. So because the question is obviously, so what do you write on that nice bus, right? So what's the information on there? And then you dive into designing structures and structured events in there. Again, that was a bit of a first for us, essentially defining which becomes an API then for the whole company. And you start off with first talking about technical stuff and evaluating technical stuff. In the end, we ended choosing Avro as a structured message format, and then the discussions really start, because then you start talking about what are the entities that you write in there? What is an account and what's its relation to our customers? What metadata do you need to transport? And does an IP address always mean the same thing? And or is it, which IP address do I write down? Is it the IP address from some proxy, from some load balancer? Do I write stuff from our middleware data in there as well? How do I identify different services in the company? How do I identify different processes in the company? And so on. So we had a lot of discussions about what is essentially, I would claim, is architectural debt. And it all came to light, because now you're having one big API and you're having lots of stakeholders and they're all quarreling about what should go in there. So this is what I found very frustrating, but I think it's also a very typical thing when you have the scenario. As I said in the beginning, you have a kind of middle to bigger sized company existing with lots of existing IT infrastructure, and you try and make this kind of change. you can then go in the details, and you can talk about different things, and you realize, oh, I'm never going to get this one version. I'll have continuous change, so I need to be able to have evolution. I need to be able to change the versions of my events. So how do I do that best? Do I follow some kind of traditional API naming scheme? What changes are compatible? Which changes are not compatible? How do I compose my events? And so on. Yeah, so a lot of talking. I think it took more than a year of talks. You also have then, once you kind of start bringing this into production, you have discussions, and you realize, well, maybe I look too much at the producer side of the whole thing, right? Because there's a conflict between producers and consumers. So the producers rather want to have an easy job. They want to write off their events and be done with it. And then you have the consumers, and they say, well, I can't, what did you give me there? I can't discern what process is this, and is this a sub-process? And in the end, did you deliver the mail or didn't you deliver the mail? I can't see this. And so you have typical other conflicts in there, like if you make it easy on the producer, for example, you might want to choose. Let me backtrack a little bit. In your infrastructure, you usually one business process goes through a lot of technical systems. So you have authentication, and then you might have a mail system that takes a mail and then tries to send it off somewhere and so on, and tries to deliver it, and then that works for one ISP, but it doesn't work for the other ISP, and so on and so on. So you have a lot of different processing steps, and so now usually the goal for the consumer is to build one coherent picture of what happened in a particular instance of a business transaction. And so now you're faced with the challenge of how do I get all those puzzle pieces together as a consumer? And so there's two different ways you can go there. You can either burden it on the producer and say, hey, you have to kind of puzzle together, and when you're done with the business process, then you give me the event. And you might need some temporary storage, like a session store or so on, to build this together, but it's your responsibility. Or you can say, no, each and every single producer in your infrastructure only writes what is his particular context. And then it's on the consumers to join all this together. This is what we chose in the end, because after a first try, the other avenue it proved to be wasn't handleable. The events got too big, and the whole thing got too unstable, and so in the end we changed it, and we said, no, it's going to be the consumers, and they're going to get a lot of different small puzzle pieces, and they'll have to do all the joining then. Okay. So as I said, so nowadays we have this infrastructure after long struggle. There's about 2 billion events per day that go through this infrastructure. It's a stack that's composed of Kafka, Avro for message serializing, Flink for processing, Influx and Redis for kind of monitoring and building up aggregates from the stream. It's not very big. It's just a couple dozen machines. Throughput is, including everything, maybe 10,000 messages per second per core or so. Very often there's things going on like testing or replays or changes to versioning. So this is another typical challenge that comes up, is that you want to have your tooling and your infrastructure be able to continuously run different versions, slightly different versions of this on the same data, and compare results and test and see if you like the change you made. Okay, and last but not least, one other important thing that we found is Kafka is a nice system and it does the job really well. But one unintended problem with this is it does the job really well also in terms of decoupling. So if you have lots of different processes that are kind of depend on each other via Kafka, sometimes it's very hard to figure out if the process as a whole works, so all the different parts. One producer might have stopped or changed what he's producing to Kafka, and it takes maybe quite a while until the last consumer has figured out that at the beginning of the process and the beginning of the queue, something went awry. And so one learning we also had is it's very important to have really good monitoring, very detailed monitoring. Also, if you use something like Flink, what we use extensively because it makes joins and windows, very typical operation, makes it much easier. Monitoring becomes a very involved question. And you have to kind of make up for all the decoupling that goes on and all the distributedness and all. So our Flink runs on a Jan, and we experiment with Kubernetes. And so all this is nice and dynamic and everything, but it makes it very involved to figure out if the system is really doing what you expect it to be doing. And the solution thus far for us means we do extensive monitoring on a lot of details, on all the different operators that are in a Flink job and so on and so on. Produces a lot of data, high load on the monitoring systems, but so far that's our best solution for it. Okay, so we did this and we felt pretty happy with it. Thought we're getting somewhere. Now we just have to implement our abuse filters on it, and we're modern and we're done. And then a while back, this happened here. So a little scatter plot there. Time on the lower axis and accounts on the vertical axis, and I don't know. Can you see it? Right? It's, the structure in there is not really healthy. So right. So because if you have all legitimate users, it's kind of random, right? So every little dot here is a transaction on a particular user account, right? So the y-axis is some kind of a projection of accounts, of account identifiers, right? And this is time. Okay. So over time, legitimate use is not synchronized in any which way, right? So it's kind of randomly distributed, and you can see that here in the background, more or less. And of course, those structures here, they're synchronized. So meaning there's a number of accounts who are somehow working in coordination, and that is not healthy. So it was kind of a funny story. So every once in a while it happens. You come into the company, and the whole company is a bus, right? So it's going on, and a left meeting and right meeting, and people sitting there with red hats and stuff. And so you go in there, and then in the end, this came out. We figured this out after a while. But the point is, we hadn't really noticed with our abuse systems. Right? This initially came out because some business KPIs went off the charts. So we had way too many Opera Mini users or something like that. So and that came out like couple of weeks later. And this is how it started. And then after the longest time, we were able to picture this and to figure out what's going on. And why did it take us so long? And why didn't our abuse systems give us a good warning of this? Is because this attacker here managed to do the attack almost perfect in the sense that he didn't give us much in terms of metadata. He came through botnet, emulated the usage well from how our users normally operate. He only made this one mistake, and that was basically he went through the accounts in a certain order. So we are quite lucky there. But of course, we realized we were missing something. And the missing ingredients for us was in our filters, we need to focus more on classifying legitimate use. Because especially when you look at metadata, the bad guys, they're always going to try and obfuscate what they're doing. And maybe if you're Google or Facebook or something, somebody really advanced and you're putting a lot of money into it, you can afford to try and classify each and every strategy that they have to kind of obfuscate and hide what they're doing. We don't spend this kind of money, so what we're missing is the initial focus on saying, hey, but legitimate use is much easier to classify. And to conclude, a simple example, what that meant for us. So if you look at essentially the geolocation and the geographic patterns according to which an account is used, right? You can take the IPs that you see and you assume you can assign geolocations to it. For simplicity now, we'll assume that we'll just ignore the very low percentage of people who come through some kind of a proxy, cascade, Tor, or so on. And when you do that, then you can obviously say, well, I assume that the usage I see is closely correlated to the physical location of the natural subject, of the natural user. And if you do that, then you can see a typical pattern. For example, for us, there was here, we have sampled some user accounts, the normal user accounts here, and abuse-labeled accounts in red. Abuse labeled by our existing kind of legacy abuse processes. And you can clearly see that your assumption is going to hold true. So, for example, you can see that the geo variance here is much higher tendentially for illegitimate accounts. You can also put this into a second dimension and say not just the geo variance in the sense of the average distance between, say, logins or something, but you can also say how many unique kind of clusters of geographic usage do I have? Because again, the assumption would be that somebody like you and me is going to show up only from just a handful of locations, usually, right? So, and this actually holds true very well. So then you can see here that most of our normal users just have a few clusters to their name, essentially. And you can imagine it's very easy to write a classifier that does well classifying this kind of chart. In fact, I had a student doing this like a couple of days ago, and he just did a regression tree, classification tree, and essentially was able to replicate the results of our existing abuse process, which is, I think, is a whole team doing this, up to about 1% in error. And if you think about it, what also turns out is that for me, I'm very privacy concerned. So the immediate question is: so if you profile your legitimate users, how does it work with privacy and data protection regulations? And it turns out if you put a little bit of thinking into it, you can do this very well. For example, similar to like hashing passwords, right? For example, this here has only 2 dimensions, right? Which are not very, don't give away a lot of privacy. Well, they might say, well, I can see you from 3 locations, right? And we tried an approach, which I'm not going to detail here though, but it turns out that instead of, say, for example, memorizing geographic locations from your users in order to build a profile, it is sufficient to transform this into a sequence of distances and angles of motion. And it turns out you can get quite the same classification performance from that. And then so now instead of memorizing and storing in your infrastructure a history of locations, what you have is a history of distances and speed and orientations. And you can build sequences from that. And this is why this was called initially geoentropy, this whole example. If you have a sequence of things, we know we can define an entropy over it, and we can define a type of surprise level that we have for a new observation. So, for example, if somebody comes and logs in from a new location, I can be more or less surprised, right? And why would I be more or less surprised? On what basis? Well, simply on the basis of I have seen that person from such a location. But I don't mean to say from a particular location, but I'll explain this. One sec. So instead of kind of memorizing locations A and B, and then I go back home and I log in again, I'm at A, and then I go back to work, I'm at B. So instead of memorizing the sequence of locations, I memorize just the distance vector in between. And so depending on if I see me log in from C, then I get a new distance vector with a new orientation, and I would be surprised. And this is essentially, the theory behind this is very simple, and it's essentially is well established from text compression and analysis. And this works out really well for us, and we don't store really the specifics of user locations anymore. Okay. Okay, so then to conclude, for us, it turns out passwords, risky, multi-factor. Yes, product management says we need this, and it's probably very important, but in the end, we don't hope to cover a large percentage of our users or our use cases. So this kind of imperfect authentication approach is, for us, the way to go. And it will also be used then to dynamically decide when it's warranted to ask for more expensive authentication factors. This kind of in-depth analysis is costly. It can be some kind of a culture change. You usually have a lot of overlaps to other stakeholders like business intelligence. So you should not expect the actual analysis to be the bigger part of the cost, but actually all the stuff around it. If you don't have the infrastructure for it, as we did, and you come from a legacy infrastructure, there's a lot of things you have to change, and a lot of things you can also pay lip service to, but you're going to pay for it later. So, for example, if you don't have a great monitoring system, you can say, well, my existing monitoring system has worked well for us, and we can monitor all our hosts with it. Why can't we monitor those jobs with it? But we made the experience that in the end you find out you pay fairly dearly for this because it's a complex system and it's loosely coupled. It takes you a long time to figure out if something goes wrong if you don't have the tools for it. Okay, and then last but not least, on the particular domain, not so technical, focus on the legitimate users first. We found it to be quite possible to do this also in a data protection compliant type of way. Okay, so that would be my talk. I didn't see any questions. All right, sure. Yes. Yeah, well, so the question was, what does data protection compliance mean for us? Well, I said that so confidently, but I think a lot of us know that the interpretation of those laws is still way out. So, what I mean by compliant is that we can regulate very well what we store. So in order to do this kind of location classification, we don't have to store long-term classification profiles. What we have with Kafka, regarding your question, is, yeah, all the raw data comes in there, but it has a limited lifetime. Okay, so we can kind of model the limited lifetime. We can increase it or decrease it, whatever our legal people say. But then in the end, for the longer term, right, if you have a user profile, if you want to kind of make a classification based on habits, you're interested in long-term time spans. And so for that kind of long-term profiles, we don't store location profiles. Not the explicit location, but some kind of mapping, right, that you can. Okay. Okay. Well, thank you.